looks great on my end. So it is my pleasure to welcome Vera Berger, who is a master's candidate in scientific computing at the University of Cambridge, where she studies computational fluid dynamics on a Churchill scholarship. And Vera will be headed over to MIT next month to do a PhD in physics, where they plan to study observational astrophysics. So Vera, thank you so much for coming out and speaking with us today. I'm excited to hear about your work, and I will turn it over to you.
Thanks for the introduction, and thank you all for having me. I interned at Goddard last summer with the TESS GI team, so I'm really excited to be back with you all today. And I'll be discussing some research that I did with my collaborators at the University of Hawaii, and I'll tell you how we used a decommissioned galaxy survey to perform the most comprehensive statistical analysis of UV stellar flares using simultaneous observations in the near and far ultraviolet. And I'll show you that 98% of stellar flares are brighter in the far UV than typically assumed by optical studies and photochemical models. For those of you who were lucky enough to have seen the aurora in May, the solar flare responsible for it is pictured here. And flares are these bursts of electromagnetic radiation driven by an extremely fast change in the magnetic field topology in a plasma called magnetic reconnection. And the term reconnection refers to the idea that oppositely directed field lines in a plasma get too close to each other and they break and cross-connect. But that breaking of lines is unphysical. Really, the plasma has neutral points in the magnetic field where resistive diffusion can happen at a much higher rate than global diffusion. And this allows for massive amounts of magnetic energy to be converted into kinetic and thermal energy. And in the case of flares, charged particles are accelerated downward into the chromosphere, heating chromospheric plasma. And all of this is observable as this burst of radiation across the electromagnetic spectrum. And the sheer amount of UV radiation is very visible in this image. It's saturating the detector. But flares on lower mass stars, M dwarfs in particular, can be 10,000 times as energetic as the most luminous solar flares. And while flares on our sun can contribute to the aurora and the occasional radio blackout, flares on M dwarfs can have a much greater impact on the planets which orbit them. So let's dive into these low mass stars a bit and see why M dwarf flaring is such an important piece in exoplanet habitability. So low mass stars have strong dynamos, which are powered by differential rotation and convection. And stars below 1.3 solar masses at solar metallicity have surface convection zones. I've denoted that in light brown here. And stars become fully convective at around spectral type M4. And we expect to see heightened magnetic activity in these stars with convective envelopes. And in addition, M dwarfs are prime exoplanet host candidates. The stars are very abundant. They make up 75% of the stars in the Milky Way. And M dwarf habitable zones are closer into the star because the stars are low luminosity, so it's colder. And that means first that it's easier to find planets in the habitable zone because it's easier to detect planets with smaller orbital radii through transits or Doppler variations. And at the same time, the majority of planets around M dwarfs are tidally locked, at least the ones that have been discovered. That percentage is in part due to observation bias, but it's a common trait among the planets that we're currently looking at that they are tidally locked to their host stars, which means the day side of those planets are really bearing the brunt of any flaring activity, which I've mentioned is more frequent and energetic than what we'd see on our sun. Now, the exact impact of flaring activity on exoplanets is an active area of research, and some really interesting theoretical work has been done to predict the impact of flaring on exoplanet environments. But I'm going to focus on two photochemical models, which observational studies have been begun to use as sort of a diagnostic of flaring activity. And to do that, we'll look at something called a flare frequency diagram, which looks at a combination, or it looks at the occurrence rates of flares of a given energy or higher. So the first model we'll look at is considering ozone depletion. This is from Matt Tilley and collaborators who used a 1D photochemical and convective radiative model. And they approximated flare emission using a UV spectrum and optical light curves from the M dwarf star AD Leo. And they found that the ozone column in an Earth-like planet could be depleted almost entirely over the course of 500,000 years of flaring, and also irreversibly. And they came up with a combination of flare rates and energies thought to be sufficient to drive this effect. And that's what's denoted by that black box in the FFD. On the other hand, we think that UV photons were necessary to drive the formation of life here on Earth. And Paul Rimmer and collaborators looked at how much light exactly is needed for UV photochemistry. In particular, how much UV radiation is needed from stars to provide the building blocks for RNA synthesis. And they also produced combinations of flare rates and energies thought to be sufficient to drive this effect. And we'll revisit some of the assumptions made in these models later, but the takeaway for now is that they're being used as a diagnostic for the impact of flaring for individual stars in observational studies. And I'll take you through placing a star on this diagram as single band optical studies typically do. Without loss of generality, we'll take a flare light curve from TESS. We have information in one red filter. How do we calculate a bolometric energy? Well, we extrapolate for the majority of the flare emission. We assume some black body temperature, typically 9 to 10,000 Kelvin. We scale the SED to match the observed flux in the band pass, and we integrate over the SED. We integrate over time to get an energy, and that gives us 1 point on this diagram. And for the same star, we try to obtain more flares so that we can reconstruct some sort of flare frequency distribution. And we repeat this process for as many stars as we can get data for, see if we land in this black or green box. You might be noticing more green lines over here. That's because the placement of the prebiotic chemistry zone depends on the temperature and the radius of the star of interest. And over the past decade, there's been huge progress in the field to study flares on the population level. Maximilian Gunther and collaborators obtained a sample of around 9,000 flares from TESS, and they calculated flare occurrence rates and energies in this way that I just showed you. And here are their results plotted, separated by spectral type on these flare frequency diagrams. And they found only 8% of sources had sufficient flaring activity to fall in the ozone depletion zone, a good number of which were F, G, and K stars. And they only found 1% of the sources in their sample to have sufficient flaring to fall in the prebiotic chemistry zone, which is a whopping 14 stars out of over 1,200 that they studied. But note that they assumed a 9,000 Kelvin black body here, and if we were to increase the assumed temperature for these flares, energy would scale significantly, and so we'd probably have more stars falling into these regions. So statistical analyses of flares have typically been conducted in single band optical wavelengths using these space-based missions like TESS and Kepler. And some of the largest flares that have been detected have come from ground-based surveys like ASSASSIN. And all of these optical surveys have provided us with large samples of flares and have allowed us to place good constraints on flare rates. But the flare energies typically hinge on this assumption of a 9 to 10,000 Kelvin blackbody, which is largely untested. And I've included a 10,000 Kelvin blackbody here in purple. And I've also added 20 and 40,000 Kelvin blackbody SEDs for reference because um, some of the few far UV flare spectra in existence have actually measured continuum temperatures up to 40,000 Kelvin. This was a work by Cynthia Froning and collaborators. And optical instruments fall on the tail of blackbody emission, where it's particularly hard to distinguish hotter SEDs. Here I've just taken away the normalization I had in the blackbody intensities, and I've scaled all of these SEDs to have the same amount of flux in the test bandpass. But as you can see, they have significantly different total energies, and optical surveys miss the majority of flare emission and the UV radiation, which we think is so important for habitability. So that brings us to the GALEX Space Telescope, which operated in the early 2000s and surveyed the entire sky save for the galactic plane. That's this white band that you see in the map here. And the GALEX detectors contain photon counters, which is actually really important because this allows us to bin data at arbitrarily short cadences and will allow us to study the temporal evolution of flares in great detail. And previous works have used GALEX observations to study stellar flares, but usually only for one or two stars. The recent creation of the G-Photon software and database from Chase Millian and collaborators made it a lot more straightforward to search for stars with GALEX observations and perform aperture photometry, and that really enabled the large-scale studies of flares that I'll show you today. And finally, GALEX performed simultaneous observations in the near and far ultraviolet, which allows us to probe these wavelengths, where the majority of flare emission is produced and which are thought to be so important for habitability. So in an effort to study a volumetrically complete sample of flares in the UV, we looked to the Gaia catalog of nearby stars, which includes sources within 100 parsec. And we performed flare detection in the near UV because the near UV detector on GALEX outlived the far UV detector by a few years. And also we expect for any black body, the near UV will be more sensitive than the far UV. And we essentially search for one point that is 3 sigma above the baseline flux of the light curve, and then 2 adjacent points in any direction that are 2 sigma above the baseline flux. And we tried around 20 variations on this detection method, and we found that this one minimized things that we thought looked like false detections and maximizes the identification of things we think are flares. And we obtained a sample of around 500 flares on 400 stars, nearly 200 of which had simultaneous near and far UV observations. And the vast majority of the stars in our sample are fully convective, which is in line with the idea that fully convective stars are magnetically active. And for now, I'm going to focus on the stars that have simultaneous observations in the near and far UV. And we're going to use those simultaneous observations to calculate color temperatures. So assuming that the entirety of flare emission can be attributed to a black body, we perform synthetic photometry on a black body of some temperature by convolving the SED with the filter response functions and determining how much flux we'd expect to see in the far UV versus the near UV. And we repeat this process for a wide range of temperatures to obtain a one-to-one mapping between far UV to near UV ratio, which is on the y-axis, and black body temperature on the x-axis. And this relation becomes asymptotic around 50,000 Kelvin, where the black body is so hot that any increase in temperature at that point doesn't change the relative amounts of far UV and near UV emission. So here's a flare light curve in our sample that's very clearly far UV bright. And at peak brightness of the flare, we see that the far UV is 2.5 times as bright as the near UV. And this corresponds to a 33,000 Kelvin blackbody, which is extremely hot. This is one of the hottest flares in our sample. But in fact, we find that 98% of the flares in our sample display color temperatures above 9,000 Kelvin. This histogram is showing that ratio at peak brightness with mappings to color temperatures on this top axis, and we have bins by spectral type. This dashed line shows that typically assumed range for flares of 9 to 10,000 Kelvin. And the median far UV to near UV ratio is 3 times higher than what's predicted by a 9,000 Kelvin blackbody. And my advisor, Ben Chappie, did some math and found that a factor of 3 difference is the same as the difference in UV you'd experience in summertime in Anchorage, Alaska to Honolulu, where unprotected skin can get a sunburn in less than 10 minutes. So that factor 3 is quite a difference. And as you can see, the scatter is quite large. A good portion of it is actually intrinsic scatter that's not attributable to measurement error. And finally, looking at these kernel density estimates that are overplotted, there seems to be some evidence that we increase to higher far UV to near UV ratios as we move towards fully convective stars. So we were inspired to search for correlations, which brings me to my next result, that we observe a tentative weak correlation of this ratio with spectral type. So here we have those same ratios plotted as a function of G minus RP color with a linear fit. And studies have shown that the transition toward fully convective stars can be subtle. And so perhaps it's not surprising to have a weak correlation. We also don't have information on the Rossby number for these sources. We don't know if these stars are saturated. So this G minus RP color is our best attempt at probing the magnetic field structure of these stars. We were also inspired to look at the trends with respect to flare UV energy. The UV energies of our flares range from 10 to the 29 to 10 to the 33 erg, which is barely getting into super flare territory at 10 to the 33 erg. And again, we find a weak correlation with low significance. Although if we go from the lowest energy to highest energy flares on this plot, we would expect the relative levels of far UV emission to increase by a factor of 3, which is not a trivial change. Some people might be wondering if we would expect this far UV to near UV ratio or color temperature to scale more strongly with flare energy. Um, Maybe not. This is a plot from a solar flare paper, which showed a similar trend that the temperature would increase by a factor of 2 to 5 when the energy increased by many orders of magnitude. So it might not be surprising that we have a weak correlation once again. So up to now, I've shown you results measured only at flare peak, but we were interested in looking at the temporal structure of flares. And because the GALEX detectors contained photon counters, we could obtain very high cadence light curves for these flares. So we constructed light curves with cadences between 10 and 30 seconds, which were just scaled by the distance of the star to optimize signal to noise. And I showed you this flare earlier. It's been at a 10-second cadence, and you can already see some interesting structure in the light curve. But we took the most classical looking flares in our samples and developed empirical templates for flare light curves in the near and far UV. I'm happy to share details on the fitting process if people are interested later. This is still kind of a work in progress, so I'm just showing the current near UV model that we have. That's plotted in cyan. against the widely used optical template for flares from Jim Davenport and collaborators. And it appears that the UV light curves have a steeper decay than the optical ones. And this trend is actually even more pronounced when we look at far UV flares. And I'll do some more analysis and estimate robust uncertainties, but this is sort of an interesting result. And with flare templates, we can start looking at the temporal evolution of the flares in our sample. This is a stacked 2D histogram with again, looking at the far UV to near UV ratio, this time over the course of a flare. And this dashed line again shows that 9 to 10,000 Kelvin temperature range, typically assumed for flares. And we find that the far UV to near UV ratio evolves over the course of a flare. In particular, it increases going up to flare peak. So the relative levels of far UV to near UV emission change as a function of phase. So if flare emission is well represented by a black body, this is showing that the flare temperature changes as a function of phase, or otherwise how line emission changes as a function of phase. But overall, the ratios fall above that 9 to 10,000 Kelvin range throughout the duration of the flare. So this leaves us with a glaring question. Are flares 50% hotter than typically assumed, or are there significant contributions from line emission, which to the total far UV flare emission? I think it's probably a combination of both, but this is a really hard question to answer. Ideally, we would obtain spectra for flares to distinguish the origins of that emission from lines versus a hot black body continuum. But the landscape of far UV flare spectra is extremely limited, with only a handful in existence. One of the first of which is from the 1980s, the Great Flare on AD Leo, which is a nearby Emdorf, which is very active. And this spectrum showed enhanced line emission, but was ultimately consistent with a 9,000 Kelvin blackbody. And this exact spectrum has been used in both of the photochemical models that I told you about earlier to approximate flare emission. And I think is a big reason that the 9,000 Kelvin blackbody has become sort of a standard. And this flare, as well as others that I found for Emdorfs, still measure a hot blackbody as the dominant emission source. But when we look to the sun, this is not always the case. This is a far UV flare spectrum of a line-dominated solar flare. And between these two spectra, there are great differences between the flare energies, the type of star that's flaring, and the spectral resolution. So it's not immediately clear the extent to which we can extrapolate from the sun. However, if we degrade this solar spectrum to the same resolution as this 1980s stellar spectrum, they don't actually look too different. So it's possible that some line emission is not being resolved. Now, let's suppose that we can attribute all of the far UV excess emission to a black body and return to this sample of nearly 10,000 flares from TESS. 60% more stars would fall in the ozone depletion region of this plot, and around 3 times as many Emdorfs would have sufficient flaring activity to deplete the ozone column in an Earth-like planet. Quantifying the impact on prebiotic chemistry is much more difficult because the photochemical model actually relied on some assumptions about flare emission that we've shown are not reasonable. And as I mentioned, both of these models are based on that 1980 AD Leo flare spectrum, which has a 9,000 Kelvin blackbody contribution. So we really need to revisit some of the baseline assumptions that both observational studies and photochemical models make to really start to understand what sort of impact flare activity could have on an orbiting planet. The future for UV flare observation for the next decade is very exciting. The landscape for UV flare spectra and photometry has been pretty limited because we need instruments in space to be able to observe in the UV. Hubble has provided UV spectroscopy. However expensive and risky it can be to observe flares. Um, Mantis will observe alongside JWST and will provide simultaneous observations spanning the EUV to the optical. And Mantis will be great for contextualizing some of the planet observations from JWST and will also survey a huge sample of low mass stars. They also have an amazing mission patch with a flaring star and a mantis shrimp, which are known for their exceptional eyesight. And I also want to mention the ESCAPE mission, which is currently proposed to observe in the EUV, and a prototype will fly on Mantis in the next couple years. So that's very exciting. EUV-ST is a solar telescope, and this will provide, for the first time, simultaneous spectroscopy from the solar chromosphere to the corona, and also flare plasmas with very high resolution, which is exciting. Ultrasat will have a very wide field of view and will be useful for near UV flare rate constraints. And then finally, UVEX will provide spectra and will have simultaneous near UV and far UV observations with 50 times the sensitivity that GALEX had. And finally, just this last week, Space Telescope Science Institute announced a program to survey rocky M-dwarf exoplanets with hundreds of hours of time on JWST and hundreds of orbits on Hubble to look at host star activity in the UV. So I'm very excited to see all the science that will be done in the next decade on this front. And I'll leave up my summary slide here. Thank you so much for taking the time, and I'm happy to take any questions.
Awesome, great talk, Vera, and awesome work that you're doing. Thank you so much for sharing it with us. So yeah, we have plenty of time for questions. If anyone has any, please feel free to raise your hand, or you can also post them in chat for Vera. I think I see one from Michelle. Go ahead.
Hi, Vera. Great talk. I was wondering how you determine like the cutoff between fully convective and partially convective stars.
Yeah, that's a good question. So for now, we're just using the G-RP color from Gaia, and saying that anything beyond M3 is considered fully convective. That's, I think, not the best way to start looking at the magnetic field structure of these stars, but since we don't have better observations, that's what we're using.
I have a suggestion if you want to talk another time.
Oh, that would be great. Okay. I'll reach out to you. Thanks.
Cool.
Awesome. Any other questions for Vera? I guess just a sort of general one. I'm not an expert in this at all, so I don't really have specific questions. Everything you said seemed great, but I guess what are some of the next steps in this work for you? Are you going to be expanding this at all in grad school, or are you kind of shifting focus into something different?
Well, in the immediate future, we're working on a paper to publish the templates for flares in the near and far UV. And flesh that out a little bit. It's looking like I'll join a black holes research group next year, so I'm not sure exactly how much I'll be able to continue this, but I have so many ideas. I think it would be really great to revisit some of the photochemical models and look at what happens if we assume a different SED for flares.
Awesome. Yeah, well, I mean, black hole flares are probably a little bit on the other end of on the scale here.
Yeah.
I see a question from Vlad. Vlad, go ahead.
Yeah, thank you for a nice talk. Yeah, so of course the far UV and UV emission are extremely important because the major contribution to the biometric energy comes from them, and of course Kepler and the optical missions underestimate the biometric energy. That's very important. So our multidimensional, multi-wavelength studies of the solar type stars also show that the biometric temperature deviates significantly from 9,000 kelvins, which it's very, very important study. Very nice. So the just one comment that if you go back to the those regions of prebiotic chemistry um, and the ozone depletion. Can you please go back to that?
Yeah.
Um,
These.
Well, yeah. So this, yeah. So I just wanna let you know that those kind of ozone depletion zone, and prebiotic chemistry zone, a little bit simplified actually, and I can say why, because they were created not by astrophysicists, by chemists. Because the prebiotic chemistry, is basically mediated by UV emission only when you already have the simplest molecules that can provide the key molecules for prebiotic chemistry that can only be obtained if you have the energies much greater than UV emission. You need the energies with wavelengths less than 1,000 angstroms in order to dissociate molecular nitrogen. So from that point of view, it's already kind of like EUV rather than FUV. So and they just basically assume that you already have those molecules, so the next complexity comes on the UV. And when it comes to ozone depletion, so ozone depletion means that you need energetic particles, and the energetic particles come from the coronal mass ejection shocks. And coronal mass ejection shocks, the conditions for coronal mass ejection shocks are pretty hard to achieve for M dwarfs because of the strong dipole field. So basically, which is good for solar type stars, but not for M dwarfs. So basically, those two regions are, the one is more representative for the solar type stars, another one is basically a conditional.
That's an important point. Thank you.
You're welcome.
Great. And I see one from Allison.
Yeah, hi, wonderful talk, Vera. So I'm wondering, I'm thinking more about the emission lines, and I'm wondering, have you calculated, the 80 Leo spectrum you showed, the lines are very, very strong. Do they dominate over that weaker continuum, or does the continuum dominate in terms of total flux?
They found that the continuum dominated for this flare. But I mean, it might have been that they're just sort of masked by having a low resolution spectrum. Even also these lines, like a lot of the lines were saturated as well. And there are more recent RUV stellar flare spectra, like from the Muscles survey. And I would be really interested to look back at those, which are presumably much higher resolution, and trying to see if we can calculate the relative continuum versus line emission contributions.
Yeah, cool. Thanks.
Yeah.
All right. Any last questions for Vera? All right. Not seeing any. Vlad, go ahead.
Just got an idea, that the question that Vera asked about how to discriminate between the line emission and the continuum emission. So the point is that if you can take, simultaneous observation with H alpha, let's say, from ground-based observations, normally because the observations in far UV, most of it should come from Lyman alpha, right? So the H alpha can serve as a proxy to it. And normally, the light curve is not that as steep. So that may, imply that most of the contribution comes from the continuous emission rather than from line emission that will be, will be highly scattered, and so therefore less steep.
Mm, that
Awesome.
makes sense. Thank you. Oh, I'd love to talk to you more about this.
Sure. Yeah, we can talk about that. Thanks.
Great. Awesome. Well, I think I don't see any other questions. So I think let's thank Vera again for the great talk. Thank you so much, Vera, for coming out and speaking with us today. Awesome work that you've done, and excited to see what you do at MIT with black holes and whatever else comes your way. But thank you so much again for speaking with us.
Thank you so much for having me. Bye.
All right.